Let's talk about linear codes in channel coding. Linear codes have inherent mathematical structure, which makes it computationally feasible to do error detection and error correction. And we can use our knowledge from linear algebra to design very powerful codes easily. Let's recap the definition of a code before we define a linear code. A code is a set of valid code words. We denote it using capital C, where it's a set of C0, C1 until C capital N minus 1, where that means there are capital N number of code words, which we call valid code words. And usually capital N is 2 to the K, where K is the message word length. The code words themselves are of length small n. Let's now build some algebra on binary numbers. We have two binary numbers, 0 and 1. So this is how we define the operator plus. 0 plus 0 should be 0. 1 plus 0 should be equal to 0 plus 1, which is equal to 1. And 1 plus 1 is 0. Note that we covered all possible combinations of these numbers. So whenever we see this symbol plus in the context of binary operations, this is what we mean. Note that this operator plus logically behaves very much like the XOR operator. Next, we will define the binary multiplication operator. We will say 0 times 0 is 0. 0 times 1 is equal to 1 times 0 is equal to 0. And 1 times 1 is equal to 1. Again, since I covered all possible combination, this completely defines the multiplication operator. Now that we have some algebraic structure, we will use this to specify parity computations as algebraic operations. Let's take as a simple example the rectangular codes. The input to the encoder is a message word and the output is a code word. Let's say we are considering 8, 4 rectangular code. That means the message word length k is equal to 4 and the code word length small n is equal to 8. The code word itself is made of the message bits, or the first 4 bits is basically the message word, followed by the parity bits. So how are these parity bits calculated? The encoder will first arrange the message bits in a rectangular form and then calculate the parity bits such that the number of ones in all columns is even and the number of ones in all rows is also even. Let's take a simple example. Let's say my message word is 0101. Then I will arrange these bits in this order. So M0, M1, M2 and M3 and then calculate the parity bits. Here are the parity bits. Note that the way these parity bits are determined is to make sure that the number of ones in all rows and columns are even. Now let's see how we can express these parity computations using algebra. Here is a simple and useful theorem. If the sum of a set of binary numbers is 0, then there are even number of ones in this set. Furthermore, if the sum is 1, then there are odd number of ones. Let's look at an example. Here I have 5 binary numbers and there are odd number of ones. And when you add them up, you get like 1 plus 1 will be 0 and then 0 plus 0 is 0. So there's basically the sum will be equal to 1. As another example, here I have 4 ones. That means even number of ones. So 1 plus 1 will be 0, 1 plus 1 will be 0, and then I'm adding 3 zeros, so the sum will be 0. So you can see the proof for this theorem is actually pretty straightforward. So I'm not going to write the entire proof, but I think it's clear. Furthermore, also observe here, it says if the sum of a set of binary numbers is 0, then there are even number of ones. The other direction of the statement is also true, that if there are even number of ones, then the sum will be 0. And if there are odd number of ones, the sum will be 1. Okay, again, I will not prove these statements because they're pretty straightforward. Here is another simple theorem. For any binary number b plus b will be 0. Note that when we defined the binary addition, we said addition operates like XOR operation. So 0 plus 0 is equal to 0, 1 plus 1 equal to 0. Right? That means if you add any binary number to itself, you should get 0. That's basically what this theorem is saying. Now let's see how we can do parity calculations using algebra. Going back to the rectangular code, we said the way we will calculate P0 is to make sure that the number of ones in this column is even. If the number of ones in M0, M2 and P0 is even, that means we should have the sum of those guys to be equal to 0. Again, this plus here is the binary addition. I can add P0 to both sides of this equation to get this equation here. Since P0 is a binary number, P0 plus P0 should be equal to 0, which gives us an algebraic way of calculating P0. We can write down the equations for P1, P2 and P3 similarly. What we have here is a system of linear equations. Now all these equations can be expressed as single equations using matrices. We have M, which is a message word, and we can collect all the parity bits into a vector and call that parity vector P. The above set of equations can be expressed using this single equation here, where this here is a matrix multiplication, where you're multiplying this vector or this row vector with this matrix. For example, the element P0, which is the first row, first column. That means you take the first row of the left matrix, first column of the right matrix and multiply. So M0 times 1 plus M1 times 0 plus M2 times 1 plus M3 times 0, which will give you M0 plus M2, which is the first equation here. You can similarly verify all other the equations for all other parity bits. Let's call this matrix A. Then all parity equations can be expressed using a simple matrix equation like this. In a valid code word, which is the message word followed by the parity bits, the message words and the parity bits are related using this equation. This is a mathematical condition we can check to identify valid code words. So for example, if we're doing error detection, if we want to check if the received code word is a valid code word, we take the parity vector and we compute m times a. And if m times a is not equal to p, then we say it is not a valid code word. We can write m as m times the identity matrix, and we can write p as m times the matrix A. Combining these two, we get another equation like this. The left-hand side is the code word C, and we will call this entire matrix here as the generator matrix. So as you can see, so if you have a message word, going from message word to code word is just multiplication by a matrix. Let M1 and M2 be two message words, and C1, which is equal to M1 times G, and C2 is equal to M2 times G, be two code words. Note that C1 is the code word corresponding to M1 and C2 is the code word corresponding to M2. Let's define M3 as M1 plus M2. Note that M3 is also a message word because all possible combination of k bits are message words because these are information bits. So if you add two message words, the result should also be some other message word. Now let C3 be the code word corresponding to M3. I can write M3 as M1 plus M2. I can distribute this matrix multiplication over the addition and I get this. And M1G is C1, M2 is G, M2G is C2. So what this means is when I take two code words C1 and C2 and I add them, the resulting sum will also be a valid code word. Note that this plus here is again the binary addition. This brings us to the definition of linear codes. A code C is a linear code if for any two code words C1 and C2, their sum is also a code word. Based on our discussion above, we can say that any coding scheme where the code words are obtained as where message word multiplied by a generator matrix, if the code words are obtained this way, then the resulting code will be a linear code based on the discussion we had here. Now, this is not the only way we can create linear codes, but if you take your message word, multiply with a matrix, and and say the result is a code word, then that will result in a linear code. In the discussion here, we created this matrix G very specifically for this rectangular code here, right? But this G could be any other matrix. So as you keep changing this matrix G, you get a different coding scheme. Then the question of asking, the question of asking what are good linear codes or what are good codes becomes translated to what is a good generator matrix, which will be the topic for our future videos.